All right, so this video is about ionic compound solubility, when precipitates form, what the concentration of the ions are that are present in the solution, and why not every compound necessarily will form a precipitate when we expect it to, or what factors influence when a precipitate will form. Okay. We look at this by looking at a different form of K than we have with our other equilibrium applications. We're going to look at Ksp, which stands for solubility product. Basically, all we do is show how that solid would dissociate into its respective ions in that equilibrium expression. The actual solubility of the different solids will depend on the concentration that is needed to get it to dissolve. Solids that are typically insoluble will have very small KSPs because not much of that solid will be able to dissociate before the precipitate will form. It will become supersaturated quite quickly. For solids like NaCl, they would have very large KSP values. We won't tend to be dealing with the ones that are mostly soluble because they're going to dissolve in large amounts before they would reach their saturation level, their solubility. Factors that can influence your solubility, your KSP values, would be your temperature, depending on whether it's an endothermic dissolution or an exothermic dissolution. And one other factor that will play a role and that can change the value of your solubility without changing your KSP is if you have a common ion present. If you have multiple sources of an ion and you increase the concentration of one of the two ions that would result in the precipitation occurring, you might not need the solubility of your salt to be as large as you would have previously. All right, so there is a change on your note sheet for this one. So I've got here an example of a dissolution reaction. It should be a double arrow, sorry, with bismuth sulfide. We see that bismuth makes 2 bismuth ions and 3 sulfur ions. And initially, if you don't have any of the solid in solution, you would just have the amount of it you have. Notice it's in moles because it's a solid. It's not going to be a part of our equilibrium expression. But however much of it is capable of dissolving would be what minus X would represent. And then because 2 bismuth ions form for 1 unit of bismuth sulfide, the change in bismuth would be 2X, and the change in sulfur, because there's 3 sulfur ions present, would be 3X. Because we're dealing with solubility, we tend to represent X in terms of solubility by writing it with an S. I don't care if you write it with the X or the S, but just know that solubility is going to be whatever the value is of that solid that's able to dissociate. So in this particular example, the solubility would be whatever X is. Now, if I was going to write the Ksp expression for this particular reaction, again, it's products over reactants. Each ion that's present or gas would be included in your equilibrium expression, raised to its coefficient. Solids and liquids do not get included, so all Ksp expressions will just be whatever the product ions are raised to their coefficients. The Ksp value that I gave you on your paper is going to be different than the one that I'm going to be using today. One, the one that was there was incorrect, and 2, you can't solve for it with that value. Your calculator can't handle it, but it was an incorrect answer. So please correct your values to 3.5 times 10 to the negative 32nd. If we know the value of Ksp, and we know what that Ksp expression is in terms of our X, in terms of our solubility, 2S for bismuth and 3S for sulfur, we can mathematically solve that through squaring the 2 and the S and 2S squared, and cubing the 3 and the S and 3S cubed to get 108 S to the 5th. Since we know the value of Ksp and we know what the expression for Ksp represents in terms of solubility, we should be able to set the two equal to each other and solve for what the actual solubility is for bismuth sulfide. and it was 2 times 10 to the negative 7th. Really small amount. Very, very little bismuth sulfide would need to dissolve before you would start seeing the precipitate form. So your insoluble solids are going to have very small Ksp values, while your more soluble solids are going to have very large Ksp values. What I have in this first example is a little bit different than what you have on yours. It's the same solid. I think I used to do 2 examples here, and I only have 1. So I just rewrote the slide so that it would represent just the one solid. Sorry about that. We're going to write a balanced equation for aluminum sulfide going through a dissolution, and then we're going to write the Ksp expression. So we're just going to practice what we did with the previous example with bismuth sulfide. In this particular one, you still have 2 aluminums and you have 3 sulfurs that are forming. So when you write that reaction, which yes, should be with the double arrow, apparently I did not go all the way through the PowerPoint on this one, you would see 2 aluminum ions form and 3 sulfur ions form. Again, your Ksp is just the aqueous solutions or the gases that are present. You were told that aluminum sulfide was solid, so it would not be included in your equilibrium expression. And again, because we're dealing with solubility, we write it with a Ksp. In our next example, you are told you have a saturated solution. So you are at equilibrium. You have the amount that you have dissolved is the solubility for this particular solid, silver oxalate. The concentration of silver in the solution that's saturated is 2.2 times 10 to the negative 4th molar. And I want to calculate the Ksp. What is the value for this solid in terms of its equilibrium constant? So to determine the Ksp, I need to be able to write a Ksp expression. And at this point, I would encourage you to go ahead and write the equation out so you know what the equilibrium expression is coming from. Silver oxalate was split into silver and oxalate ions. There's 2 silvers that are present and 1 oxalate. Apparently, I went ahead and did this part first. Sorry about that. We know that silver's concentration is 2.2 times 10 to the negative 4th. That was provided for us. We'll come back to that in a second. Again, it should be a double arrow. I don't know what's up with me with the arrows. So silver oxalate would produce 2 silver ions and 1 oxalate ion. So the Ksp expression would be the silver ions squared and the oxalate. Now, if silver, there were 2 of them produced from 1 silver oxalate molecule and only 1 oxalate produced for 1 silver oxalate molecule, that concentration of silver would represent 2 times the solubility of silver oxalate. So that would be your 2x. And then the oxalate would be just x. When we go through and do this mathematically, we get that S is 1.1 times 10 to the negative 4th. Again, because silver is in a 2-to-1 ratio with the silver oxalate compound, the concentration of silver that's dissolved is twice the amount of the silver oxalate that was able to be dissolved. So S would just be the 1.1 times 10 to the negative 4th. If I know the value of S and I know my Ksp expression in terms of S, I should be able to solve for Ksp by substituting that value in place of S. And when I do that math-wise, I get that the Ksp for this particular solid is very small, 5.3 times 10 to the negative 12th. The next question we are asked to do is to determine, going backwards, to this last one, we found the Ksp from the solubility. Now we're going to find the solubility given the Ksp. You're told to ignore any acid-base properties because phosphate is a conjugate base. So if you had pH that could influence, or pH other than 7, it could influence the solubility of that compound. If we want to find the solubility of strontium phosphate, we need to be able to write its Ksp expression in terms of those ions. My hope is you're starting to notice a pattern. Your Ksp will always be the two ions, the cation and the anion, raised to the amount of ions present in your solid. So if I had used a double arrow like I should, you would get that there are 3 strontiums and 2 phosphates that are formed from strontium phosphate. So your Ksp expression would be the strontium ions cubed and the phosphate ions squared. What we also know is that 1 strontium phosphate makes 3 strontium ions and 2 phosphate ions. So in terms of the solubility of strontium phosphate, strontium would have a concentration of 3 times the solubility of that solid, and phosphate would have a concentration of 2 times the solubility of strontium phosphate. When I math it through, make sure you cube both the 3 and the s and that you square both the 2 and the s. I get that the Ksp expression in terms of s is 108 s to the 5th. I know the value of Ksp, it was given to me, 1 times 10 to the negative 31st. So if I go through and mathematically solve for s, I can get the solubility of strontium phosphate, 2 times 10 to the negative 7th. If I had asked you for what strontium's concentration would have been, it would have been 3 times that, so 6 times 10 to the negative 7th. And phosphates would have been twice that, 4 times 10 to the negative 7th. So you were asked to find the solubility of your solid, so you're just finding S. If you were asked to find it for either of the ions, you would need to account for how many of those ions are present once you reach equilibrium. Our last mathematical problem for this section, you were given the Ksp for silver sulfate, that it's 1.2 times 10 to the negative 5th, and you're asked to determine what the solubility is of that compound if it's in a solution containing 0.1 molar silver nitrate. Why would that be important? Because you have a common ion. Both solids contain silver. So silver nitrate is providing us with a source of silver ions, 0.1 molar to be specific. Again, double arrow. Silver sulfate would break into 2 silver ions, or be able to dissolve into 2 silver ions and 1 sulfate ion. The Ksp expression would be the silver ion squared along with the sulfate. I know what my Ksp value is, and I know that I have a source of silver ions, 0.1. And I know that if the silver sulfate was contributing to the silver ions, it would increase by 2s, and the sulfates would just be s. I will tell you that when you have a common ion, and if you look at the value of your Ksp compared to that concentration of silver, you see that they are off by a 10 to the 4th. You are going to be allowed to exclude that the change in solubility, that 2s, is going to be negligible compared to the concentration of the silver ions that are already present. And because silver is present in such a large quantity, the solubility of silver sulfate is going to be much smaller than what you would have expected it to be without those, because you won't need as much of the sulfate to reach that K value, to have Q equal to your Ksp. So we're going to solve for S, the solubility of this particular solid, by assuming that the concentration of silver is not going to change appreciably, with it already being at a fairly large quantity, 0.10 molar. We would square that quantity. We don't worry about the 2s again. And then we would solve for S, and we get that it's a value of 1.2 times 10 to the negative 3rd. I'm pretty sure I put this in the calculator and it did not appreciably change. If you had accounted for the 2s and solved for it graphically, I think you still would have gotten this answer. 0.0012 would not even have influenced the sig figs for that 0.1 molar concentration. If we had not had the silver ions present in the form of silver nitrate, we would have expected the solubility to be much greater. We would have expected more of the silver sulfate would have needed to dissolve to reach that Ksp value. So having a common ion can reduce how much you need of the particular solid to dissolve before precipitation occurs. The last question that we're going to talk about in this section, I used to do the mathematical part with this, but we only have to discuss it now qualitatively, is what would happen if you had some of these solids in solutions that weren't neutral, that were in acidic solutions or basic solutions. With that in mind, the acidity or basicity, if there are ions present whose concentration would change depending on the pH of that mixture, that can influence what the solubility would be for those particular solids. So we're looking for solids that are acidic or basic, that have conjugate acids or conjugate bases making up their solid, or in the case of a strong base, have hydroxide present, because all of those are ions that would be influenced by the pH of a solution. So with our first three, they all contain silver. So silver is an transition metal. It's not going to be influenced by pH. We saw that metals in general, other than like highly charged metals, aluminum, iron, I want to say we said aluminum, iron, copper, things like that, but silver is not one of those that's influenced by pH. Fluorine, chlorine, and bromine. We know that chlorine and bromine are coming from strong acids, but fluorine is coming from a weak acid. So if the pH was acidic or basic, that would influence the solubility of that salt because fluorine's concentration would vary. So AgF would be the salt in that particular set of three that would be influenced by pH. In the second set, we have PbOH2 and PbCl2. Hydroxide, being from a strong base, would absolutely be influenced by pH. You could neutralize some of that hydroxide, or you could increase the concentration of the hydroxide present. So PbOH2 would be the salt that was influenced by pH in that particular example. And that would be the end of ionic compound solubility.